Hello, hello, AP Calculus BC, and welcome back to our exploration of polar equations. I originally hadn't planned on throwing derivatives in here yet, but I think they made a little bit more sense here, and that way we can, when we do our explorations of more polar graphs the next 2 days, keep incorporating derivatives, make sure you're comfortable with everything, and then we will finish with integration and area. So let's get started. There's a nice opener here, so why don't you go ahead and try all 4 parts, and once you're done, unpause, and we will go through it. Ready, set, go. Alrighty, how did we do? Well, we have a derivative expression that we're looking for at the beginning, dr d theta, so hopefully we were comfortable, even though we haven't done this before. At this point in your time with calculus derivatives, we should have seen that to create dr d theta, we do d theta of each side, right? Something like this. Okay, and that will give us dr d theta over here on the right side, 0 plus 2 cosine of theta times the derivative of the inside, but because we're with respect to theta, it's just right there. So I think we just get 2 cosine of theta. Exciting. Evaluate dr d theta at theta equals pi over 6. Okay, we can do that. Dr d theta evaluated at theta equals pi over 6 will give us 2 cosine of pi over 6. Get to practice your trig values here. We need to realize that cosine of pi over 6, let's see, sine of pi over 6 is 1/2, so cosine's got to be root 3 over 2, and simplifying gives us square root of 3. What type of graph will this make? Well, that one's kind of out of left field. We saw graphs of polar equations all the way back to day 70, I think, and you don't have to know these perfectly. In fact, you don't even need to know this off the top of your head. Eventually you will. But what we discussed is that if the coefficient that is adding is larger than the coefficient that's multiplying, then you will have and remember these were called limicons, right? This little C thing, I think it's called like a cetyle, and I'm sure my pronunciation is not great there. But we have our limicon, and it's going to be without an inner loop. Yeah, I think that's what we'll have, probably around the upper portion of the y-axis because of sine. We'll check that in a second. Actually, let's check it right now. Have this ready on Desmos. There we go. Yeah, looks pretty good, right? We call this a cardioid if it bounces off the center over here. A cardioid is our specific subset of a limicon, and cardioids occur when these two values are the same, right? So if it was 2 plus 2 sine, it'd be the cardioid, look like a heart. This one looks like, I don't know, a fatter heart. But either way, we call it a limicon without an inner loop, just to be easy. So, moving on to our last part. Interpret your answer from part B in context of the graph of r equals 3 plus 2 sine of theta. Ooh, tricky, tricky. So what are we saying here? Well, we're saying if we evaluate the derivative at pi over 6, what does pi over 6 mean, and what does the square root of 3 mean? Well, we know theta is pi over 6, so in terms of our graph, let's see, we did something like this. Pi over 6 is kind of right about here. I'm just going to draw a little radius, and we can stop anywhere on that radius, but there's pi over 6. There's going to be some specific point there. We'll just put the point out here. I'm not sure what r is. Couldn't we find r, though? I think we probably could, right? We could find the distance that r makes just by doing r equals my original equation, 3 plus 2 sine of pi over 6, and we'll need this later, so it's not a waste of time. 3 plus 2 times 1/2, 3 plus 1, which is 4. Okay, so then this line that's extending out, I don't really like to make it solid. I don't want us to think there's a line there, but this line has a distance of 4, and there's a point floating out there. If we wanted to see it on our graph, Desmos unfortunately doesn't really have a good way to graph polar coordinates yet. It can do polar equations, but not coordinates. So I had to change my polar coordinates to rectangular. Again, a good throwback. To find the x, we do r cosine of theta. To find the y, r sine of theta. And if I turn that on, we'll see our point out here. This, from the origin to the point, is a distance of 4 and an angle of pi over 6. Great. So we have that point, but what did dr d theta tell us? That's a weird one, right? We got a positive answer, a positive derivative. If we interpret dr d theta, we're saying as the angle of theta changes, then how is r changing? Or more specifically, at pi over 6, how is the radius changing? Well, we got square root of 3, so what that's telling me then is the next point that's really, really close to this will have changed by square root of 3. Technically, it should be right on top of it if it's square root of 3, but for now, we're just going to assume that that means that if we go to the next point, our r has increased by a length of square root of 3, which is actually a pretty big increase. So at this exact point, the radius is increasing or changing at a rate of square root of 3. We could say radius units per theta if you would like. So every theta you move, you are moving by square root of 3 radiuses. Radians? Not radians. Radius lengths. Sure. All right, so again, it's just that idea as one thing is changing, in this case as theta is changing, how fast is the radius changing, and the radius is changing by this amount. A little bit tricky, and over the next couple days we're going to dive a bit deeper into that concept, especially the next 2 classes where we do more on rose petal graphs and limicons with inner loops. For today, though, we're actually going to finish off, and I know, super quick lesson today, I'm sure you're sad about this. We're going to finish off with how we create tangent lines from polar equations. Now we know that to find the slope of a tangent line, we are going to build our usual equation, t of x equals like f prime, I should write it this way, dy dx, evaluated at some value times x minus some value plus some value. Tangent lines are always in the form of y equals x, but what are those values? Let's start with the derivative, because that is the most involved process. The derivative for a polar function is not necessarily tricky, but it's a little arduous or maybe tedious because there are a bunch of terms. I'd say that the derivative of a polar function does not come up very often, maybe once on the multiple choice. Very unusual to see it on the free response just because it is a bit of a longer process. So how does it work? Well, we're going to go back to our old friend parametric derivatives. Okay, and with parametric derivatives, we said to find dy dx, we did d dt of our equation of y, and then we did d dt of our equation of x, which would be great, except our y and our x equations, do we even have y and x equations for polar? Well, hopefully you're saying, oh, yeah, we remember those identities. We actually just briefly touched on them. X is created by r cosine of theta, and y is created by r sine of theta. So when I'm looking for d theta of y over d theta of x, that means we're going to be taking the derivatives of these two identities. Now you might be saying, how come you're doing d theta instead of ddr? Because there are both of those variables there. You could do ddr if you would like, but ultimately our tangent line is going to almost always be written as a function of theta. So they're going to say, find the derivative at some value theta, and then minus an x value of theta and a y value of theta. So theta is going to be our general input. Theta is the input. And if you think about normal tangent lines, right, our normal tangent line uses x as the input. So it should make sense that we're going to use theta here instead of r. You could have used r if you'd like. It just might be less useful in the long run. So what does this mean? In order to find dy dx for a polar equation, we do d theta of y, d theta of x, and then we can, of course, substitute, because we know that y is the same as r sine of theta, and x is the same as r cosine of theta. But, unfortunately, we're not done there, because we actually need to take those derivatives. Now, don't forget that r is connected to our trig function either to sine or cosine through multiplication. So what rule do we need to use? Well, that's right, we need to use the product rule. So I've actually already run through the derivative for you here. Just in the interest of time, you can follow it, but you're going to be doing it a few times, and I thought it was maybe a little I don't know, rude of me to ask you to write it out more than you had to. So let's follow along with this derivative. We started here, and we'll keep those same colors where y is in green. We use the product rule. So to do the product rule, we do the derivative of the first function first, which is dr d theta. And then we keep the second function the same. First function the same, derivative of the second function. Same for the denominator down here, right? So we're going to do the derivative of the first function first, keep the second the same, now do the derivative of, or keep the first the same, and then the derivative of the second, noting that because we're doing the derivative of cosine, a negative is introduced, and so it is quite common to see this reduced down to this form where the negative takes the place of the positive. Now, this is a derivative that I would suggest you do not memorize. It doesn't come up enough, and it's not important enough to memorize, but you do need to be able to find it if asked for. And how do you do that? You remember your parametric derivative. Parametric d dt of y over d dt of x, and then you compare it to polar. d d theta of y divided by d d theta of x. Those are both how you find dy dx in your respective forms. You do, however, need to know that this is x, this is y. Once you make those substitutions, the product rule makes it easy to get to that derivative. All right, one example with a couple pieces here, and then you guys have 5 practice problems, and we're done. Find dy dx at the given value of theta. We're using the same equation from the opener, actually, this limison without an inner loop, and we want to know the value of dy dx at theta equals pi over 6. Okay, well, we're going to need to know a couple things. Eventually, we will need r, and we'll need dr d theta, which is interesting, and you'll see why shortly. Okay. We just went over the original derivative equation, dr d theta, sine, plus, and so on and so forth on the previous page. But now, we're actually going to substitute to make this more specific to our problem. In particular, we know that r is the same as 3 plus 2 cosine of theta, so everywhere we see an r, we need to substitute 3 plus 2 sine of theta. You can always do this later on in the process, but I find it's easier to do at the beginning so we get everything in terms of theta. Don't have to worry about r's or dr d thetas. Speaking of, dr d theta, 2 cosine of theta, we have 2 substitutions to do there. And now we're looking pretty darn good. I don't know why I did all of those. 1, 2. Ha! But we're not done yet. This is the general equation for dy dx as a function of theta, but they asked us to find the value of dy dx evaluated at pi over 6. So what do? Oh yeah, replace all of our thetas with pi over 6. But the nice part is we found both cosine and sine of pi over 6 several times so far. So I think we should be okay here. A lot of this is simplification, and we can take you through it if you'd like, but don't forget you really don't have to simplify, as long as you remember that cosine of pi over 6 is going to be square root of 3 over 2, and sine of pi over 6 is going to be 1/2. Then you can simplify down as far as you'd like. You can just write those in and you're set there. And hopefully you know by now, but you don't even need to simplify those. If this was a free response question, which it probably would not be, but if it was a free response question, you could literally stop right here and box this whole answer and say, haha, I win. Because that is something you could evaluate in your calculator and get an actual number. I did go through some simplifications and you can see if you can follow it. It's nothing too terrible, right? Square root of 3 over 2 times 2 we already saw was square root of 3, so that's where that guy came from, and we had already said the sine of pi over 6 is 1/2, and so on and so forth. Okay. Finishing this off, though, I did give us a decimal approximation of our dy dx evaluated at pi over 6, and I think you'll see why in just a second, too. Okay. And actually, I think even before we do this last part, let's talk about the decimal approximation. What is the interpretation of this guy, dy dx of pi over 6? And is that different than, remember we found dr d theta at pi over 6, right? We said that was square root of 3. I think square root of 3 is definitely different than a negative value over there, which has lots of weird stuff going on. Why are they different? Do they mean different things? Well, of course they do. This is telling us how fast y is changing as x changes. And it's saying, as x is changing by a bit, y is increasing, or in this case, I'm sorry, y is decreasing at a rate of 3.8185. So it's giving us an interpretation of x and y, but using theta as an input. So this is actually doing what we did in Calc AB the whole time through. This is our new thing for today. Now, can we go a step further? Hopefully. Why don't you take a quick second and use the information we already have here. We've actually done almost all of the math for you. And please write the equation of the tangent line in the form of y equals f of x, which passes through the polar curve. And when I mean the polar curve, I mean r equals 3 plus 2 sine of theta, the same one that we've been using, when theta equals pi over 6. Try that, and then we will unpause and see how you've done. Okay, hopefully you've had some success here. What we're really trying to do, and we've mentioned before, is we're writing this tangent line, and we're saying t of x here. There is going to be x, but then the question becomes, what are all of our different values? Well, we're going to need to know dy dx at what? Well, they gave us an input at pi over 6. Okay, times x minus x of pi over 6. Whatever input you use for here, you're going to be using that same input for the rest, plus y of pi over 6. Luckily, we already know one of these. We just went through the whole process and found this derivative. This derivative is this guy up here. And you can use your decimal approximation. I'll use the exact value just because it makes me happier. So square root of 3 plus 4 root 3 over square root of 3 minus 4 times. What about these last two? Well, do we know an equation that will turn thetas into x's or y's? We almost do. I think we know, and I highlighted these on the previous page, we know that x is our cosine of theta and y is our sine of theta. So how do we use that? Well, oh wait, we know pi over 6 is theta, and we have an equation that turns thetas into r values. Our thetas into r values is the original equation. How do we use it? Well, let's go through the process. We know that x is equal to r cosine of theta, and r was equal to 3 plus 2 sine of theta. Good so far. I think we're only going to need to use the r equation once, so in fact I probably should have written this over here, apologies. So we know r is equal to 3 plus 2 sine of theta, and the only theta we're interested in this problem is pi over 6, so let's find r of pi over 6. We actually did this earlier. Looks something like this. So r of pi over 6 is 3 plus 2 times a half, 3 plus 1, which is 4. I'll get rid of this guy. Now I think we have enough information to figure out x here. X is technically a function with two inputs. So if you wanted, you could write this as x of r comma theta equals r times the cosine of theta. I don't think that's too common, but it is good practice with function notation. And so we are really, even though they want to know what is the x value at pi over 6, we're also using the r that we just found. That was 4. And so we get 4 times the cosine of pi over 6, which is 4 times the square root of 3 over 2. We do a little reducing, and we get 2 square roots of 3 for our x value. And then the same for y. We know, we'll go a little faster here, that y is also a function of both r and theta, and it is r times the sine of theta. So we get y of 4 comma pi over 6 takes the same two inputs, and this is in the same spot, 4 times the sine of pi over 6, 4 times 1/2, which is 2. And there's our tangent line. Maybe not the most beautiful tangent line we've ever seen, but we should probably make sure that we're correct too. Okay, so I think I have this pulled up on Desmos here. Let's double check. There we go. So we have the point in question. Looking at this point, if you envision a tangent line, the tangent line certainly has a negative slope. What is that negative slope? Oh yeah, it is our negative 3.8185, or this fraction monstrosity over here. So I think our slope makes a lot of sense if we bounce a tangent line off of it. And I actually have the tangent line prepared, and you can see how I wrote it over here. Okay, I just did our dy dx, and then I used the two formulas for x and y. And when I turn this on, look at that, perfect little tangent line. Alrighty, what do we have left to do? Well, if this was an actual partner activity, I'd ask you to go through this. I think we can just talk it through, though, and you guys can probably take notes quickly. Your goal, though, and maybe you're working together, is to understand the difference between dr d theta and dy dx in the context of polar graphs and polar equations. So if you are working with a partner or you're just on your own, why don't you take a quick second, pause me, and see if you can jot down what dr d theta will tell you about an equation versus dy dx, and then we'll talk it through after. Ready, set, go. All right, we're back. Dr d theta is pretty easily found. You just do d theta of each side of the equation. Right, we saw that on the opener for today. It's measuring how fast the radius is changing as theta changes. And looking at the graph over here, this was a radius of 4. Notice on the y-axis, this is a radius of 5. And what's happening with this graph is we have a radius that goes out and we put a point at the end. And then we bump up just a little bit and we go out over here and put a point at the end. And then go out here, another point at the end, and so on and so forth. And what's happening, if this is 4, this is going to be a little more than 4, a little more than 4, close to 5, really close to 5, and then here is at 5. And so while the radius is getting longer, dr d theta, which measures how the radius is changing, will be a positive value. We started with a radius of 3 over here, so dr d theta is positive, 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 till we get to 5. But then look what happens after 5. Now my radius is getting smaller, and so if we found dr d theta of a rotation in the second quadrant, let's say 2 pi over 3, something up here, then our dr d theta would be negative because the radius is shrinking, shrinking, shrinking till 3, shrinking, looks like it's still shrinking till we get to 1, and then we start growing again around the other side. So dr d theta is just measuring what's happening to the radius that is creating the points on the outside. Versus dy dx. dy dx is just our attempt to be able to write tangent lines. It's showing us what's happening as x and y are changing. So if we treat this as an xy grid, which it is, right, it's just telling us the steepness of the point on this graph. So hopefully that was a fairly clear summary for you. Dy dx is definitely more of a monster to find a derivative for than dr d theta. Dy dx is much less common, I think, than dr d theta, but it does come up, and you do need to know how to do it. So 5 practice problems. 4 of them are all about finding dy dx. Of course, you want more of that practice. And you actually end up finding dr d theta in the process too, so it's 2 for 1. And then the last one I think is a really good problem. They give you this graph here. I'll even show you the graph, 1 plus sine of theta. Delete all this really quickly. R equals 1 plus sine of theta, right? And you'll notice that this one is a cardioid because our two values, 1 and 1, are equal to each other. So we call this a cardioid. And their question is find the 4 points of horizontal tangency. Horizontal tangents, very interesting. And so your goal is to go through and figure out where you'd have 4 horizontal tangent lines. Now, full disclosure, I only see 3 here. 1, 2, and then 3. We know that this is a sharp point and it probably won't have a tangent line, so think about that as you go through and create your graph. It is a good application of finding dy dx when we're talking about tangent lines. We should always be dealing with dy dx, and it also gives you some practice on solving trig equations. As always, I do have the solutions written on Teams, so thank you for your time and good luck with these derivatives of polar equations.